Okay. 1576, this is a nice one. First try it and keep trying it. And when you finally get it, then that's great. Or if you get close, that's great. Please, with all these videos, try it yourself and then see how we can solve it. Okay, so we have a single ball here. It's dropped down, it hits the ground, and it rebounds. It starts at a height of h0 and it rebounds to h1. Okay, it's very simple. The question is, what is the coefficient of restitution between the ball and the ground? What's the coefficient of restitution? So the ball falls, hits the ground, comes up. Okay, so just like I always do, I go straight for the money. Okay, you want the coefficient of restitution? Here it is. E is VB2 minus VA2. So it's the difference in velocities between the two particles over VA1 minus VB1. Okay, great. Now, what does this mean? It means, first of all, we need two particles. We need particle A and particle B. Particle A, particle B. What is so we know that the one particle is the ball. That's easy to understand. What is the second particle? Well, the second particle is going to be the ground or the earth, right? And whenever you have these kinds of problems, our assumption is that the earth, at state 1 and state 2, the earth's velocity is 0. So let's call the ball particle A and the ground particle B. So our assumption is that the particle B's velocity at 1 and at 2, before and after impact, is 0. Okay? Alright, so that simplifies this, and we have E is then, so VB2 and VB1 are both 0. So we're going to have minus VA2, and we're going to have VA1 here. Okay. So that's the first step, is to recognize that our assumption is the velocity of the earth, the ground, is 0. Okay. Now, that's not the final answer. You say, well, great, we've solved it. No, you haven't solved it. We now need to find expressions for velocity of A at 2 and velocity of A at 1. Okay, so now I don't want you to get confused with the numbering. This is how I'm going to number it. I think it works. Yes. Okay. This is how I'm going to number it. At the top, I'm just going to redraw it. Let me redraw it here. The ball is at the top, and then it begins to drop. And right before it hits the ground, it's still moving down. So we call this time state 0. We call this state 1. Then it hits the ground and rebounds. Okay, and now it's moving up. We call this state 2, and then it rebounds up to that height. So that height is h1, and that height is h0. Okay, so it goes down, falls down. It impacts the earth, the ground, and it rebounds and it moves up to a height of h1. So right before the ground is state 1, and right after it hits the ground, it's state 2. And I think that makes sense, because remember, guys, your coefficient of restitution, if you're looking at A1 and A2, or initial and final, it is right before it hits the ground and right after it hits the ground, or rather right before impact and right after impact. Okay, so don't get confused with these velocities at 0 and let's call this 3. 0 and 3. 0 and 3 have pretty much nothing to do with the coefficient of restitution. The coefficient of restitution is only right before impact, right after impact. Okay, so now we need expressions for VA1, which is the velocity of the ball of A. We need expression for the velocity right before impact, and we need an expression for the velocity right after impact. So what are we going to do now? How are we going to solve this? We can use the principle of conservation of energy. So let's look at the conservation of energy between point 0 or state 0 and state 1. So T0 plus V0 is equal to T is equal to T1 plus V1. So the total energy, which is the total kinetic energy plus potential energy at state 0, is equal to the total kinetic energy plus potential energy at state 1. Okay, so what is the kinetic energy at state 0 of this particle? It's 0 because the velocity is 0. What's the potential energy? It is mgh0. mgh0 is the potential energy. And then we know that the kinetic energy is maximum. It's half mva1 squared, right? And the potential energy at this point is 0, plus 0. Okay, so if you solve for this, then you're going to get VA1 is equal to the square root of 2GH. That's what you're going to get. The square root of 2GH. Alright, that is the magnitude of this velocity. Okay? Hope that makes sense. So now we've got an expression for it. Now, we still need an expression for VA2. We carry out exactly the same thing. T2, now we're going to move between points 2 and 3. T2 plus V2 is T3 plus V3. The initial kinetic energy is half mVA2 squared plus 0 potential energy is 0 kinetic energy plus mgh1. Did I get that right? This is h0 here. h0, h0, h1. Okay? Again, if you solve for this, you're going to get VA2 is the square root of 2GH1. VA1 was the square root of 2GH0, and VA2 is the square root of 2GH1. So E, which was minus VA2 over VA1, is then equal to, now, minus VA2, but basically we can choose up as positive, because remember these are vector equations. Well, we need to choose a positive direction. So the height was positive upwards, and so the velocity needs to be positive upwards. So this velocity A1, okay, well, if we look in the denominator, the velocity A1 was moving down, which means it's negative. So we're going to have a minus 2GH0 square root. And at the top, we are going to have 2GH1 square root. And so these minuses cancel. And we're going to end up with the square root of H1 over the square root of H0, or H1 over H0 square root. Okay? And does this make sense, guys? Try to critically evaluate this. Does it make sense? Yes, H1 is lower than H0. So H1 over H0 is going to be less than 1. And then the way that the mathematics works out, it is the square root of that number. So yes, E is less than, this is less than 1, which makes sense because it doesn't rebound all the way back to its original position. There has been some loss of energy. Okay? So that's the answer. E is equal to the root of H1 over H0. Okay, cheers.